Hey there. You've definitely seen that classic logo for an atom, right? You know the one, a little ball in the middle with a few other little balls zipping around it like tiny planets? Well, what if I told you that entire picture is just wrong? Today, we're going to tear that old idea down and find out what an atom actually looks like. Okay, so let's just dive right in with the big question. That picture we all have in our heads, that tiny little sun of a nucleus with electrons spinning around in these perfect, clean circles, is that for real? Do electrons really orbit the nucleus like Earth orbits the sun? And the simple answer is no, not at all. Not even close, actually. The truth is so much weirder, and honestly, way cooler. So let's dig in and find out exactly why that old model had to go and what the mind-bending reality really is. Now look, if this whole topic has ever made your brain hurt, I promise you, you're in good company. This quote just nails it, right? Going from that simple little solar system model to what we know now, it really does feel like you're learning a whole new language, because in a way you are. But don't worry, stick with me. We'll figure it out together. To really get a handle on where we are today, we've got to travel back in time a bit. Our story kicks off around 1913 with a physicist named Niels Bohr. He came up with a really simple, but at the time, totally revolutionary idea of what was going on inside an atom. So let me break down Bohr's big ideas for you. First, he said electrons are stuck in these fixed circular orbits. A great way to think about it is like seats in a stadium. You can sit in row 1 or you can sit in row 2, but you can't just float somewhere in between, right? No row 1.5. Second, each of these orbits has a specific energy level, kind of like floors in a skyscraper. The higher you go, the more energy you have. And third, he said electrons can do these things called quantum jumps between floors. But, and this is key, it's like an elevator that only stops on certain floors. You need the exact right amount of energy to go up or down. And here's the crazy part. For a super simple atom, like hydrogen, which only has one electron, Bohr's model was a home run. It worked perfectly. It explained exactly why hydrogen gas glows with very specific colors when you heat it up. It was a massive breakthrough. So, if the model works so well, what was the problem? I mean, why didn't we just call it a day and stick with this nice, tidy little picture of the atom? Well, as soon as scientists tried to apply it to anything more complicated than hydrogen, the whole thing fell apart. It just didn't work for atoms with more than one electron. It also couldn't explain some other weird details, like why certain colors of light were brighter than others. But the biggest problem, the real fatal flaw, was its core assumption that an electron was just a simple little ball following a predictable path. That was about to be proven very, very wrong. And that's when physics got a complete makeover. Seriously, things were about to get wonderfully weird. This was the beginning of the quantum revolution. Just think about how fast everything changed. We start with Bohr's model in 1913, but then, just over a decade later, guys like Louis de Broglie and Werner Heisenberg show up and basically flip the whole table over. The rules of physics were being completely rewritten. And this brings us to one of the wildest ideas in all of science, wave-particle duality. De Broglie proposed that an electron isn't just a tiny particle, it's also a wave. Think about that. It can be a solid little thing in one spot and a spread-out wave of possibility at the exact same time. It's bizarre, but it's true. Then, building right on top of that, Heisenberg comes along with his famous uncertainty principle. Now, this is crucial. He proved that you can never, ever know both the exact position and the exact momentum of an electron at the same time. It's like trying to photograph a moving car. If you use a super fast shutter speed, you get a really clear picture of where the car is, but you have no idea how fast it's going. But if you use a slow shutter speed, you get a blurry streak that shows you its speed and direction, but you can't tell exactly where it was at any single moment. It's a fundamental trade-off. And that right there was the final nail in the coffin for Bohr's neat little orbits. I mean, think about it. If you can't know an electron's precise position and its momentum at the same time, then there is absolutely no way you can know its exact path. And if you can't know its path, the whole idea of a fixed, predictable orbit just evaporates. It's impossible. So, if electrons aren't circling around in orbits, then where in the world are they? Well, this question brings us to the modern picture of the atom. And it's not a picture of certainty at all. It's a picture made of clouds of probability. Okay, this is it. This is the big idea. We have to throw out the word orbit and replace it with a new word, orbital.
An orbit was a simple, flat, 2D path like a train stuck on a track. An orbital is completely different. It's a three-dimensional region of space, a cloud, that tells you where you're most likely to find the electron. It's less like a train on a track and more like a cloud of bees buzzing around a hive. We've moved from definite prediction to statistical probability.
So yeah, you can think of an orbital as a probability cloud. It's basically a 3D map of possibilities. It doesn't tell you where the electron is, it tells you the region where it's most likely to be found if you were to look for it. The denser the cloud, the higher the chance of finding the electron there. And we can describe these different probability clouds using a set of what are called quantum numbers. It's basically an address system for every electron in an atom. For our purposes, the two most important are these. First, the principal number, n, which tells you the main energy level or shell. You can think of this as the city the electron lives in. And second, the azimuthal number, L, which tells you the shape of that cloud, its orbital. This is like the specific neighborhood inside that city. And these neighborhoods, these orbital shapes, get pretty interesting. The simplest one, the s orbital, is just a sphere, nice and easy. Then you get the p orbitals, which are shaped kind of like dumbbells or figure eights. And as you get to higher energy levels, like the d orbitals, the shapes get even more complex and beautiful, often looking like clover leaves. All right, we have covered a ton of ground here, right? We've gone from a simple little solar system all the way to these weird, fuzzy clouds of probability. So let's just take a second and do a quick recap to tie it all together. So what was our journey? Well, we started with Bohr's simple planetary model with its nice, neat orbits. Then we saw the cracks appear. It really only worked for hydrogen. After that, the quantum revolution changed everything, showing us that electrons are actually these fuzzy things that act like waves. That led to the uncertainty principle, which made fixed paths totally impossible. And all of that brought us to where we are today, the modern view, where electrons exist in these three-dimensional probability clouds we call orbitals. So I'll just leave you with one final, kind of mind-bending thought. If an atom, and that means everything, you, me, the chair you're sitting in, if it's all just mostly empty space defined by these fuzzy clouds of probability, what does it even mean to touch something? The crazy answer is you don't. You never actually touch anything. What you feel as solid is just the electromagnetic repulsion between the electron clouds in your hand and the electron clouds of the object. Pretty wild, right? Something to think about. Thanks for exploring the modern atom with me.